All right, hey everybody. Last study group for topic 2. Although next week we still have some office hours for our project. So don't forget to get your blogs in. Try to do it by today. If not, early next week is fine. But I will be checking in. I'll be pinging you if I don't see your blog submission for phase 1 at the end of today. Also, Monday is off, just in case you haven't seen that. Our Monday is off, and I might have to cancel one of our office hours. So I'll keep you all updated, but I think I might have to take away our Tuesday office hour. I just have to go to a doctor's appointment during that time. So I might be canceling that, but I'll update you all in the channel. So yeah, don't forget Monday's off, Tuesday maybe off. So I will, yeah, I'll keep you all updated. And Friday is your presentation for your project. So don't forget that as well. Other than that, just waiting on some blogs. I think about half of you all have gotten it submitted. So thank you for that. I've rated a bunch. I've read through a bunch of them this morning. Super enjoyable reads. And yeah. Okay. So happy to take any project questions after this as well. But let's get into our final topic, which is extensions to linear models. The main bulk of topic 20's labs are about interactions and polynomials, which are the last couple of things I want to talk about. But before that, I'm going to talk about a little bit of a review, just to really hammer down what's important from the past couple of topics. And then we'll get into cross-validation, as well as bias variance trade-off, which are kind of connected to that whole train test split thing we were talking about. So to get into that, let's start with a quick review of our linear regression so far. So this I took from the very end of our last study group from topic 19. This is basically a linear regression that's gone through a bunch of transformations, and we'll have our output. So taking a look at that, just to review some of the important things to take away from our linear regression output from stats models. First of all, our R squared. Again, remember, I really do want to see an interpretation of R squared, contextualized if you can as well, for your project. Maybe not for every model, but at least for your final model. So interpret your R squared. Also, interpret some of your coefficients. Now, I know that these numbers over here are because they are all scaled. And so from this, because I can see that horsepower has a greater magnitude than displacement and weight, I can conclude this by saying that horsepower has a greater negative, or just a greater effect on miles per gallon compared to all the other variables that we're using here. Also, p-values. Here you can see that we have a couple insignificant p-values. And remember, we do not want any insignificant p-values in our final model. We want every p-value to be below 0.05, because if we have a p-value above 0.05, it is that probability that the relationship between that variable and the target is spurious or happening by random chance. So we do not want that. Other than that, everything else you can sort of interpret in the context of regression, but those are the main things to really look at, to really look at via this output. Also, especially with your final models or whatever your milestone models are, or intermediate milestone models are, you want to take a look at your normality and your homoscedasticity assumptions as well. Does anyone have any questions about this stuff? And this is all stuff that we had covered at the start of the week.
Yeah, just a quick question. What's the minimum R squared that's considered good?
Yeah, that makes sense. I would say that there isn't really a threshold. I think for linear models especially, it's kind of, you just want to work your way up from some baseline. I would say more than 0.5 is good, because anything less than 0.5, then you can't really explain too much of the variation. You're not even explaining half of the variation in your target. So I say maybe 0.5, but there are scenarios in which 0.5 is understandable, because you're balancing a lot of different things when you're doing regression, right? It's not just R squared. There's also RMSE that you're looking at. And at the same time, you have all of your assumptions. So sometimes you're going to have to sacrifice some R squared for to maybe fulfill some assumptions or to get a better RMSE. I'm going to talk about that a little bit in the next section as well. But
Okay.
yeah, there's no like agreed upon threshold.
Okay.
Nice. Anything else? Okay. So again, I just copied and pasted the bunch of interpretation. This is exactly the same thing from the last study that we had. Okay. This section is on cross-validation, and cross-validation is kind of an extension of chain test split. So when you're doing a chain test split, remember we just randomly shuffle and put 80% of our data for training our model, 20% of our data for testing the model. So the problem with this is there is a high possibility that your model will kind of overfit to that 80%. So the training and test mean squared errors and the R squared might strongly depend on how the training and test sets were created. Maybe by complete random chance, you got all like the high valued homes in your train set and low valued homes in your test set. And now when you're testing your model, you're going to have very varied results. So I'm running a simulation over here, and this is just a quick simulation. What we're doing here is we're running 20 different linear regressions, all with random train test splits. And what we're doing here is we're going to do train test split, fit on the train set, make predictions on the train set as well, and then test on the test set. And then we're just going to look at the mean squared error. We're going to look at the mean squared error across both our train and test sets. Another thing to note here, the test size is 0.33, but for this purpose, it doesn't really matter what the test size is. So when we plot our training and testing errors, and in this case, we're using the mean squared error between the actual and the predicted, we see that there is quite a good bit of fluctuation. So this is not, these numbers are not like going in any order. These are just 20 different simulations of linear regression. And you can see that our error just really jumps around. Like the training error has a smaller bound, like sort of between 8 and 10.5. And our testing error fluctuates a lot more. It fluctuates from about 7 all the way to 12. And so this fluctuation just means that our model is not very consistent. It's fairly sensitive to changes in the training data, which is not typically what you want. So something that you can do is do what's called a cross-validation. And so how cross-validation works, and I'm just going to show you all with this example over here. Let's just say that this red bar is our data, and we can split it into 5 parts, 20% each. I'm just going to roughly 20% each. So each of these is 20% of our data. So how cross-validation works is if you're doing for cross-validation, you tell it how many folds you want. So how many subgroups do you divide your data into? In this case, we are doing a 5-fold cross-validation, 5-fold cross-validation, and cross-validation is CV. So 5-fold cross-validation just means you're going to train and test your model 5 different times. Each time training on 4 parts and testing on 1 part, and that 1 part that you test on is just going to keep changing. So the first time you run your model, this will be your test set and the rest will be the train. Second time you run your model, blocks 1, 3, 4, 5 will be training, 2 will be testing, and then so on and so forth. You just take turns running different train test splits just to see how sensitive is your model to changes in your training data. Now, ideally, if your model is generalizable enough, the error values across all the folds will be fairly consistent. And what consistent means really depends on the context. And in this case, we're running it on I think we're running it on the same data, right? Yeah, we're still running it on our miles per gallon data. So I forget what scale miles per gallon is measured over, but we can use this cross-validation score function from scikit-learn to run cross-validation for us. So in this case, you can tell it what kind of scoring you want to look at. And in this case, it's negative mean squared error. And then we have our model. And this is the model that we want to use. I use linreg, which is linear regression. Feed it my X, my Y. here I'm giving it 10 folds. Actually, let me just do 5 for now. 5 folds, and we're going to print the results and take a look at its mean. So running this 5 times, we get 5 different mean squared errors, 5 different negative mean squared errors. And so you can see that it fluctuates quite a good bit from 5.4 all the way to 27. So there is quite a good bit of sensitivity to their changes in our data set. Now, sometimes there's not much that you can do. And I think at this point, like with the knowledge of machine learning that we have now, there's not much that we can do about it, but it's good to take note. It's really good to take note if you have this kind of sensitivity, because this is the same data set. This is all from the same data set, just using different segments of it. And training and testing on different segments of your data shouldn't give you that much variation in your error. And that's what we're seeing here. I mean, it also depends on context. Like this is also squared error, and I forget what like miles per gallon looks like. Hold on, let's take a look at what miles per gallon. So miles per gallon is done on, let's do a dot describe. All right, so miles per gallon has a range of 9 through 46, and this is a squared error. So let's do a quick square root. I wonder if we do this, that works. Okay, cool. Print this, and then we'll do a square root of that to see what the actual error is. Okay, so now we're looking at errors that range from about 2 to 5. So those are our error values. And again, it really depends on the context, whether a difference of 2 to 5 for your error metrics, is that a significant difference? Is that very sensitive or not? Really depends on context. Like if you're talking about miles per gallon, some of the same model fit on different parts of your data gives you a very low error of 2.3 miles per gallon. However, on some parts, it might give you a 5.2 error. So again, really depends on context, whether you consider this to be sensitive or not. But if you're looking straight from, I would say some things that you can use to consider, take a look at like the min and max values, average values. I think the standard deviation is also good to look at. Typically, it's pretty good if your standard deviation is, if your errors are lower than your standard deviation. So just some numbers that you can think about and consider. But most importantly, think about it in context. Like these numbers by themselves have very little meaning, but you have to say, okay, this is the literal like miles per gallon average error from your model. Any questions about that? Oh, another thing before I move on, you can also use different scoring. So here you can actually feed in R squared. So you can see that with 5 different folds, the R squared really does vary. You can see here that we have some of it going as high as 0.839. And apparently one fold here has an R squared of like 0.247, which is not good at all. So again, it shows that there is a lot of sensitivity to your data in this model, which at this moment, we can only say there is some sensitivity. There's not much that we can do to directly counter this as of right now. Any questions about this? All right, let's delete that drawing real quick. Okay, so kind of related to the fact of like, how sensitive is your data to, how sensitive is your model to different parts of the data? Kind of related to that is the bias variance trade-off. So let's talk about bias and variance and the relationship between over and underfitting. So bias variance trade-off is actually a very, very commonly asked data science interview question. Often a question is like, okay, can you tell me about the bias variance trade-off and what are like implications that having high bias or variance will have on your model? So let's talk about bias first. Now, bias you can also think of as underfitting. So bias just happens when your model cannot learn its training data, nor can it generalize to new data. So bias just arises when the wrong assumptions are made when training a model. So for example, if an interaction effect is missed, and we'll talk about that later, if we didn't catch a certain relationship, and because of that, our algorithm just misses relevant information and relevant relationships between the predictors and target. So underfitting. So here is an example of a high underfitting, high bias model, right? If this is what our data looked like and we tried to fit a linear regression through it, that's not going to fly, right? Like you can see that one is not going to predict well on our training data. And if I had any additional test data points that came from that data set, probably also not going to do very well either. So that would be underfitted. On the other hand, we have overfitting or variance, and that happens when a model learns the training data too well so that it does not generalize to new data. So what we actually saw here, where our R squared was very, very variable, that is often a result of overfitting to a specific segment of your data. So you can sort of think about this, and the fact that it's so sensitive is that the model that you built is overfit to that 80% of your data, which might be missing some information that's in that 20%, or it might be over learning some things that are actually not important in the grander scheme of this data. So yeah, overfitting or variance arises when a model is too sensitive to small fluctuations in the training set. So like we just saw above. So when variance is high, random noise in the training data is modeled rather than intended outputs. This is overfitting. So that's actually one thing that is also important to think about. If you have too much random noise in your model, like for example, a lot of outliers that you're trying to account for, a lot of outliers that you're trying to fit your model on, your model might learn patterns from those outliers that you might not intend on having it learn. So that's something to also keep in mind as you're doing your data cleaning, as you're doing your culling of data, culling of features as well. So this is more of a conceptual section. Any questions about this? Awesome. All right. So after this, there's just two other techniques that you can definitely apply in your projects, in these upcoming projects. So one is interactions and one is polynomials. They're both quite similar. The idea of interactions is both of these are actually feature engineering methods where you're making new features. Remember how I talked about in your last project when you were doing that movie data set, a feature that a lot of you engineered was profit, because profit wasn't something that was provided. Rather, you engineered that feature out of the budget and revenue columns. So similarly, you're making new columns out of existing columns in these next couple of sections. In brief, interactions are just multiplying features with each other. And then polynomials is just multiplying features by itself. So taking the square of a feature or the cube of a feature. So in brief, that's what we're doing here. Okay, so interaction variables. When is a good time to use interaction variables? Usually if you feel like, one, you don't have a very linear relationship between your target and a specific variable, you might think, okay, maybe I'll get a better linear relationship if I multiply some features together. Maybe I get a much stronger linear relationship. And also when you think that you want to account for different segments of a feature. So in this example, we're going to look at, and we're using the miles per gallon data set again. We're going to look at older cars and younger cars and see if that could be made as part of an interaction. So what I'm going to do first is I'm just going to split up my data between the older and younger cars. I'm using these index numbers because I just know that's when like I cut off cars from 70 to 75, 76 to 82. And one way to test it really quickly is to take a look at two regressions, one that's only fit on the older cars and one that's only fit on the younger cars. So the code here can be a little bit confusing, but we're basically starting with two empty linear regression models. So that's what this step is here. When you're using scikit-learn for your modeling, you always start with an empty model. And this step is known as instantiation. Instantiation. Okay. So what we're going to do here is we're going to fit our data. And here we're just going to look at the relationship between like horsepower and year. And we're going to take a look at between the old and the younger cars, what is the relationship between horsepower and miles per gallon? Just to see whether between the old and young cars, is there a big difference in, just the way that they interact with the with horsepower and also with the target variable. So I'm fitting horsepower and miles per gallon for each of the models. So this is both the older car data and this is both the newer car data. So we're doing .fit here, and then we're doing .predict. And then just to see, we'll take a look at their coefficients for horsepower versus miles per gallon. Cool. So right off the bat, we have these two predictions and we're getting these two coefficients. And remember, coefficients just tell us about the relationship between variable and target. And in this case, our variable was horsepower. And you can see that between our young and our old cars, the relationship between horsepower and miles per gallon is quite stark. Like for our regression, what is our older cars? For our older cars, each 1 unit increase in horsepower brings down miles per gallon by 21. But for our younger cars, each increase in horsepower brings down miles per gallon by 35. So that's one quick way to see, like, if you already have some sort of hypothesis to start of like, okay, I think that yes, we are given all of these years, but I think there should be some sort of threshold in which we want to divide our older and younger cars. So if you want to bin your variables in any way, that's one way that you can check to see whether that will be impactful for your model or not. So another way that you can look at this is
what would be a good way of like deciding when that point is that something should be considered an old car versus a new car?
Yeah, that's a great question. I would say I would only use this method if you already have a hypothesis or an idea of what that threshold is.
Okay.
Yeah. So after this, I'll talk about it a little bit. No, actually, yeah. If you're working on a data set that you are not familiar with, like for example, like this housing data set was just provided to you all. If you're not as familiar with it, a very common practice, and you will actually see this in your labs, is to just try all the interactions together, which can seem like a lot, but there are methods of like, picking out which of the interactions. So let's say you have 10 variables, and if you want to pair up every single variable, that's what, 90 different pairs. I don't remember if I think that's 90 different pairs, but yeah, 90 different pairs, which means you're introducing 90 different features into your model, which is a very automated way to go about it. And that's typically the way to go if you're not as familiar with the data that you're using, or if you just have a lot of data and you don't have the bandwidth to go and like explore, okay, for this column, based on contextual knowledge, think we should separate it like this. Now in your labs, I don't have that here, but in your labs, there are a couple methods that you can use to iteratively select features. So there is, I think, a function that I'll source which labs those are, and I'll post the links in our Slack channel to look for the code that will basically help you do this feature selection process, because it doesn't make sense to just interact everything with each other and then just use all of it and then slowly cull one by one. Right. But yeah, it really depends. Like in the real world, typically you would do more of this approach because at your job, hopefully you know your data set better, and you can start making these like more educated, informed decisions on like what should be interacted with each other. But there are automated ways to do it as well. That's a great question.
Can you please go over one more time where you reshaped the horse values from -1 to 1, but not
yes.
the
MPG? You mean this one, right?
Correct, yes.
Okay, let's see, why do we do this? Oh, okay. I think it's because, actually, let me just check this real quick. I believe because this comes out as a series. Yeah, okay. So if I do, does this work? Okay. This is a little finicky thing. And you might encounter this if any of you are trying to do a prediction function. So the way that these .fit and .predict methods work is you have to give it a data frame or a 2D array, especially for the X values. You need to give it a data frame or a 2D array. So because of that, you can see that the series itself, when I pull out just a single column, this is actually a 1D array. There's a difference between doing this and doing this, and see how the shape changes. The shape goes from 180 comma nothing to 180 comma 1. So that's actually a transformation from a 1D array to a 2D array. And for scikit-learn, and actually I think that's the case for stats models as well, your input data must be of a 2D array. So
is miles per gallon a 2D array? Sorry, I don't have that.
No, that's okay. Miles per gallon is a series because your Y is just one variable, so it knows that it can take in a series.
Got it. That's right. Okay.
Yeah, and just to go more into that, since we're talking about it now, if I were to try and do this, they're actually going to show me an error that will, oops, here we go. They're going to spit out a value error that will tell me expected 2D array got 1D array instead. And I basically gave them this like 1D long array, and they don't really know what to do with it. So they actually tell you right down here, either reshape your data using this if your data has a single feature, or this if it contains a single sample. So in this case, we're just using a single feature. So we're going to do it, reshape it like this. If we reshape it the other way, and actually just take a look at what this looks like. So this basically looks like it's a long form reshape. If we did it the other way around, I think you want to do -1, 1. And I'll tell you all what -1 means again. And you can see how this is slightly different. See how previously each number was sort of in its own mini list, and in this case, it's all in one list. And this, the dot shape, will be 1, 180 versus 180, 1.
Thank you.
You're welcome. What this -1 means is when you're reshaping an array, and reshaping is actually pretty neat. If I had like a NumPy array, I think we're going to have time, so I'm going to spend some time talking about this. If I have a NumPy array that looks like this, and I know it has 4 values, this NumPy array looks like this, right? I can do a reshape to make it into something with 4 rows and 1 column. And what the -1 does is, if you don't want to define the second dimension, the -1 will help you reshape it accordingly. Let me give you a bigger example so it makes sense. Okay, so right now I have this array here, which is 4 by 2. So 4 by 2, I have 8 elements. Let's say I want to, instead of 2 columns, I want to have 4 columns. So I'll do reshape dot -1 and then 4. So the -1 just allows it to be fluid, just so it does the division automatically for you. -1 is just like, you don't want to define the other shape or the other dimension, and then you're fine. So because if I put like 1, if I mistakenly put 1, this is cannot reshape array of size 8. Same thing if I put like 3, cannot reshape. If I put 2, that's technically the correct dimension shape for 8. But if I don't want to do that calculation, I just put -1. And -1 will just say, all right, I just know it has to be 4 columns. We'll deal with the rows later. So that's little nuances about reshape. And why we're using reshape here is because a series by itself, and let's just look at that again, a series by itself is only 1-dimensional. So we take a look, values.shape, it is only 1-dimensional. There's no (1), which is why we have to put the dot reshape there. We give it the 180, (1). That's like a little finicky thing that I also took too long to figure out when I was learning this. But yeah, I'm glad you brought it up. Okay, so back to this, _1. Okay, so we saw that the coefficients for the 2 groups, the older cars and the younger cars, are quite different. Like I think there's more, yeah, there is more than a 50% difference between the 2 coefficients. So that means between the older cars and the younger cars, there is a fairly different relationship between their horsepower and miles per gallon. Another way that we can look at it is taking a look at the scatter plot between older and younger cars. And so this is pretty much the same information as we had over here, but you can see that for the younger cars, there's a much steeper slope, steeper negative slope of -35. And for older cars, it is not as steep. So you can see that for the age of cars, you could look into dividing that into 2 groups. Alternatively, you can also turn it into an interaction variable, and the interaction variable will also help you take that distinction into account. So let's just test this real quick. If we test this, and we're using this as a baseline real quick, I put this here just to show y'all that there's different ways of doing cross-validation. But basically, this is doing cross-validation with k-fold. And this cross-validation up here is by using cross-val score. just different ways of doing the same thing. And you'll encounter a bunch of that as we get through this program. But anyways, it's just a different way of doing it. We get the cross-val score using CV cross-validation, and we get our baseline R squared of 0.832. So let's just add in our interaction variable of horse times model year. So I'm just going to add a new column to our data frame and call it horse year. And I'm just going to add that into our linear regression. So with that, our baseline R squared has gone up by about 3%. So just by adding this one additional feature, our baseline R squared went up by 3%. If you remember what I talked about regarding R squared from before, you know that adding any features just naturally makes your R squared go up. So let's check out the stats models output. Okay, so with this stats models output, we'll see that horse year, great, it is significant. And horse here is also significant, model year is also significant. Cool. So I've gotten this question a couple of times of, let's say I'm interacting variable A and variable B, and I'm making an interaction variable called AB. If I interact the variable, do I need to get rid of the A and B, the ones that were not the ones by themselves? Do I have to get rid of that? Answer is, it really depends. Sometimes when you make an interaction variable, it causes the original variables to become insignificant. In that case, yes, you want to take it away. Sometimes it is the addition of the interaction variable that actually makes your model work better. So it's actually accounting for that one variable kind of like 1.5 times, if that makes sense, which sometimes is better for your model too. So I would say, look at your outputs before you make any decisions about whether you want to drop them or not, because sometimes you have to, because they become insignificant because of redundancy, and sometimes you don't have to. Questions about interactions? I'll source the lab that has the code for like adding a bunch of interactions. There's also like some automated code to create all the interaction variables for you, which is nice. So yeah. Okay. The next thing I want to talk about is polynomial regression, which is kind of the same thing. You can sort of think of it as you're interacting it with itself, but more specifically, it's kind of like a transformation as well. For a very, very simple explanation of polynomial regression, I'm going to use this data set of yield, just temperature and yield. I don't even know what this data set is, but you can see that there's a very obvious nonlinear relationship going on here. If I run a baseline regression, and you can see here, I'm fitting my XY and I'm doing my predict here. If I fit a baseline regression, this is how my predictor line looks, which is not good. If we take a look at our R squared score, our R squared score is 0.08, which is awful. That means only 8% of the variation is being explained. And that's because one, it already off the bat did not fulfill our linearity assumption, which is why it didn't give us great results to begin with. Also, this is our root mean squared error of 373. And I believe that our yield has already a very small range. So let's take a look at that real quick. So yield.describe. Right, yield already only ranges from like 2.1 to 3.7, and it already has like a 373 error. So that's like 10% error. So therefore, sometimes this does take a little bit of background math knowledge to understand, but there's also a way to automatically check for this, and I'll talk about that later in a bit too. But based on this, if anyone is familiar with, I guess, math and functions and calculus, if you see a curve like this, one way that you can basically characterize this as a quadratic relationship. So if you see something that's like this, right now you're like, okay, temperature and yield are not linearly related, but there's a chance that temperature squared, T squared, is linearly related with yield, which is what we're going to take a look at. So what we're going to do here is we're literally just going to add a temperature squared column. And so now our X consists of temperature as well as temperature squared. Now, after we add that, let's take a look and see what our regression line is. Because this is technically a 3D, sorry, there's technically two inputs, temperature and temperature squared. That's why it doesn't look like a straight line, but accounting for another dimension of X, it is a straight line. Now we have a much better fit. This is still a linear regression, just plotted in 2D, which is why it doesn't look like a straight line. Hopefully that doesn't confuse people too much, but you can safely say that this is a regression output. So just by adding the squared variable, we sort of allowed the line to fit our data a little bit better. And then we can take a look at our prediction scores. We now have a root mean squared error of 0.2156, which is much better than 0.3731. And our R squared also has gone up by a lot. Instead of 0.08, like 8%, we're now up to almost 70%. So just by adding that squared variable, it helps your data achieve that linearity assumption. Therefore, your model does better. You can also take a look at the summary. Again, same question holds, like if you're squaring a variable, do you want to keep the original or not? Depends on what your output says. And in this case, they're both significant. So you can see that temperature squared, one increase in temperature squared will increase your yield by 0.0012, and regular temperature will bring it down. So yeah, in this case, we would not drop this, but there are definitely some instances in which you will want to. Questions about this? Okay, so
Just
but I
a
wanna
quick
show-
general
yes.
question about, so is it a given that anytime you drop something with a p-value of 0, you're
Mhm.
going to do harm to your model?
Every time you drop something with a p-value of 0, you do harm to your model. Not necessarily. I would say one example is with multicollinearity. If you know that, let's say, two values are multicollinear, but your model gives one of them a high p-value and one of them a low p-value, and you drop the lower one, the higher one will also do better typically. Also, if you just think that in context, it doesn't make sense to use such a feature, I would say that's even more reason to take it out versus a high p-value. Because let's just say you're trying to predict the price of a house, and one of your features is, I don't know, oh, I can't think of something. One way to contextualize your problem is your features are inputs to make a prediction output. So for any input value that you have to make sure that you can actually attain that number. For example, I can only think of these examples because this is what other students are doing. For example, there are some capstone projects that are using headlines to predict stock prices. And so when you're trying to predict the stock price tomorrow, a lot of their training data is using headlines from the same day. So let's say I wanted to today predict stocks for tomorrow. I will not have tomorrow's headlines to make that prediction. Instead, what you should think about then is, okay, maybe instead of using the same day's headlines to predict stocks, I should use the day before. And so therefore, if I'm trying to make a stock prediction for tomorrow, I'm going to look at today's headlines, which I can attain to make a prediction for tomorrow's price. I hope that wasn't confusing, but
I think I got it. Thank you.
Okay, yeah, you're welcome. So basically, yeah, there's a lot of contextual thinking going on. For example, I had one person for this project, a couple cohorts back, just engineered a variable of price per square foot, which makes sense to be a predictor for price, and it's actually not going to be, it shouldn't be multicollinear or anything. But price per square foot, you can only get price per square foot if you have price, right? So imagine I'm trying to make a price prediction for a house that isn't even built yet. How am I supposed to know the price per square footage amount to input into my model to predict price? So that's something to think about as well. Dimitri's original question was, is it bad to drop p-values with, is it bad to drop variables with low p-values? I would say it doesn't really matter. If there's a variable that is like meaningful for your model, but you don't think it's meaningful in context, I would say it makes more sense to drop it.
Thank you.
You're very welcome. What I was going to show you all with regards to automatically creating these interaction terms is there is a scikit-learn method called polynomial features. And I believe in your labs, they should show you how to use this. But polynomial features actually allows you to create all interactions and polynomial features, which is pretty neat. So given all of your x columns, you can just feed it into polynomial features, tell it what degree you want it to do. You can also do interaction only. So that means okay, I'll talk about that later. But let's say you do degree equals 2. That means it's going to do interactions of every pair of variables as well as every variable itself squared. So that's what degree equals to 2 means. You can also do degree equals to 3, but I think that will blow up your number of columns. So usually for this project, folks don't do that. And then you can choose whether you only want to do interaction or not. So I believe in your labs, they'll show you how to do this. So yeah. And then you'll have a bunch of columns in which you can start doing your feature selection for. And I'll source those labs that have those feature selection methods for you. All right. Cool. That's all I have to share for today. Anyone have any questions? All right. Well, if there are no questions, let me switch off the recording and we can get into our weekly